knew and did a lot of things, and now he did a lot of schooling. So I kind of labeled what each part means. You should as well. You're going to have to plug into this on your text and follow the reason for this application here.
Ms. Baldwin, do you know what they're constructing outside of your classroom?
Yeah, is it gonna be a building or what?
Building?
Is it the new building for the school?
I'm sure. But why is it like? Cause then what are they building by building 2 and 3?
I thought they were building something at 6.
Like a new one, or are they going onto it? They're building a new
Is it gonna have
cafeteria.
bathrooms inside of it? No.
Wait, so like, how does that like? So yeah, so they like breaking down the whole town. So like, it will be done by like next year.
Oh no, because remember they're doing the whole like you remember in the library the functions that they have?
No, not really. Actually, I do, but like the loop.
Cool. Here it is. An important application of cooling. This law states for a cooling substance with initial temperature T0. So this is capital T with a little zero. This is always the initial temp of a substance. In physics, you see velocity sub zero a lot. The little zero is like the amount of time that has passed. So initial 0 time has gone by. The temperature T after T minutes can be found using this formula. T with the R is the temperature in the room, the surrounding temperature. R is the rate of cooling. Little t is the amount of time that goes by. And then there's CR, yeah, so you see the same number twice. So there's an E here. E is used for continuous compounding when interest is added all the time. So if you think about a liquid cooling or a substance cooling, of course it doesn't like cool for a second, stop, and then cool for another second and stop. It doesn't cool in intervals, it cools continuously. So it's like a continuous cooling, just like continuously compounding something. So let's look at how the formula is solved. It's really not that different from the pink paper we did yesterday. This is Alicia, an Ethiopian stew. The stool is done cooking at 212 degrees. I didn't realize their stews got that hot, but I believe it. The temperature in the room is 70 degrees Fahrenheit. The stool cools 4% every minute, so it cools pretty quickly. The soup will be cool. So how long will it take the cool stool to serve to be the serving temperature of 100? Does it make sense that we would want to serve food at 100 degrees? How hot is our mouth?
That's a good question. Maybe like
98.9. 98.9. So if our soup was 98 degrees, it would be room temperature, like tap water. We don't want room temperature soup. We want our soup to be 100, which is 10 degrees higher than our mouth. So what? That's 2 degrees higher than our mouth. 2 degrees higher than
So this is cool. It's like
I bet one time I scalded.
man, just put it in like for a minute, taste it, and then if you want to hold.
We don't want scalding.
pop it in.
So let's see. All right, so 100 is the serving temperature. We only want our soup, I guess, 100, right? 212 is how it starts. So the temperature of the room goes here, 70 degrees in the room. E is a number, 2.71. It's cooling at 4% each minute. And then we put 70 in here again. So how do we solve it? Well, the subtraction's pretty easy. And then we'll take the 70 and subtract 70 over. Divide by 142. And then from here, we have to use our skills of solving. We'll do log both sides. I would have written log E, but that's the same as ln. And then from here, we're relying completely on our calculator. So Natalie, it's going to take 34 minutes. So actually, much longer than doing this problem. 34 minutes before the stew is ready. We are now going to do
Isn't that waters down the pot, dude?
One ice cube for me.
Just wait like a couple.
we're doing number 15 on page 609.
So why don't you write it down, Kayla? Oh, we already have that paper in our thing. Kayla, look what I have in that bag.
Page 609, number 15.
No.
I have it in the slide.
You know how small this is? Yeah. Yes, I do. I can just go on lunch though.
Alright, you're driving on a hot day and the car overheats. This will happen to older cars. It's not really that uncommon. So, if you're ever driving a 15-20-year-old car, it happens from time to time. You put coolant in the car to help it cool, and sometimes it needs a new radiator. Okay? So, the car overheats to 280 degrees. If any of you are mechanics or have worked on cars, when it's hot, it'll sizzle your skin. 280. Apparently, your car can go ahead and drive when it's still 230 degrees Fahrenheit, so pretty hot. 80 degrees outside. It's really not that hot outside compared to how hot it gets here. The cooling rate is 0.0058. So this engine cools much slower than the liquid soup. Okay, it's taking much longer for this engine to cool than the soup when I compare the R value. How long will you have to wait till your car is ready to go? So please take a moment and try to plug these numbers in correctly to the formula.
Would you do this on the side of the road?
You would do this if you were a mechanical engineer and you were designing an engine.
Oh, so if you're stuck on the side of the road.
Yeah.
See how long it would take basically.
I had it pushed. Mine did the same.
I don't know.
Car,
I mean,
blew up, so I had it. It was only able to be cool, drive for like 2 minutes.
Oh, yeah.
The house was right down the road.
That's it. Yeah, you're right. Because the point is, when it gets cool, you're not gonna be able to drive it anywhere anyway. So you leave it there. You get coolant, or you give it towed to the mechanic. So this is more for honestly, like mechanics. I keep thinking of like roller coasters overheating for some reason. Because sometimes you're lined up with Sheridan's and then they're like the ride is shut down and you wait anyway, and then it opens up again in 45 minutes. Anyway,
I do that, but it's
usually when.
I only like 10 minutes.
Like,
no, it's taking too long.
Shut
Going.
down. I'm just plugging in. Did you do it? I think 5 people are playing, so I'm gonna move forward. Alright, my goal, my temperature that I want to achieve is 230, so I put the 230 in the T spot. I get that memorized right now. Wow. Alright, there is really only one unknown. There's only thing that we don't know. One thing we don't know, and it's this little t. That's what we're trying to figure out, is how much time needs to go by. So I was able to plug in for everything else given here. My goal, my starting temp, the temperature outside, E is a number, my rate was given, and then that temperature outside goes in 2 spots. The only unknown is the amount of time that needs to go by. So some pretty easy subtraction here. This will go down to 200. I like to put in a multiplication dot next to the parentheses. And then, of course, I want to subtract the 80 over, get that out of the way. You do everything you can to simplify your equation. Now we're at 150. My next move. What are we gonna do next? Anybody? What do you do next?
Can you take off the 200?
Let's take the 200 off. Let's divide that 200 off. It's in the way right now. Get it out of there. Remember, E is the base. You're trying to isolate the base and the exponent. That's as simplified as you can get. So we were able to do the parentheses. We were able to move the 80. We're able to divide the 200. And this is where we're stuck. Now we have to use a new skill. We need to solve for an exponent, so we better do a logarithm. We're going to do log on both sides. So the base is E, so we'll do log base E on both sides.